wanted to start off today just with a lot of examples based off of the stuff we're doing, and to get you guys started on a little bit more of the homeworks, because I kind of want to like narrow your guys' focus over this last week. I definitely don't want to like overburden you guys. So I was looking at homework 14, which is due on Monday. So I can kind of get you guys started on some of those, as well as tell you some other ones which probably aren't needed to do. Let me take a look. So we were finishing yesterday with arc length. Wanted to do one more example of arc length. And let's see, I wanted to do number 6 from homework 14. And then, yeah, do number 6. And then we'll do another example. I was thinking about doing number 10, but number 10 is a good arc length problem. And it's the only real arc length problem that is on the homework. So I definitely want you guys to do that. I'll do a different example in terms of arc length. The arc length problems can get, the integrals themselves can be kind of bad. And it looks like a lot of the book problems, they just set up the integrals and have you set up an integral for arc length and then have you use a calculator to compute it. So I want to be able to like do one where it's at least fully workable by hand with all the techniques of integration and everything. Because a lot of those you just can't do, and then you use technology, which isn't helpful for exams and midterms. So let's take a look. So if you pull up homework 14, if you want, let's actually start off with number 6. So this is backstepping a little bit because this is a basic parametric one. And it simply asks us to find a parametric curve. So find a line parameterized between the points 2, 3, 2, 3, minus 4, 2, 5, negative 2, negative 4. Sorry, let me make sure that's focused. There we go. And I'll get you guys started on it and let you guys finish the last one. And maybe do like the X and Y coordinates. So this is just points in 3 space. Nothing extremely new there. It's just like we are adding an extra dimension. And so instead of a Cartesian plane, we have the Cartesian space. When we model 3-dimensional space, we usually have our x-axis pointing out at us, y-axis to the right, and the z-axis to the top. So the process of getting into 3D stuff, not necessary. We're not going to need it for this class, but just to kind of see one example. All we're asked to do is find a parameterization between 2 points, namely parameterize a line. And the thing we can always take advantage of, a line can always be parameterized. By linear functions. So all your x of t, your y of t, z of t can be lines. It's not always the case. I mean, if you can have other parameterizations of the line, particularly if the fact that if I have a straight line, if I am moving along the line on constant speed, then that'll be this linear parameterization. But sometimes we are speeding up, and if we're speeding up along the line, there might be other parameterizations to model that. But since we're just asked to find any parameterization, we might as well find a constant speed linear parameterization of a line. And so really all you have to kind of think about is, well, let's just see a 2-dimensional one. if I am moving along this line at a constant speed, how is the x-coordinate changing in time? Changing at a constant speed. Likewise, the y-coordinate changing at a constant speed. How do we measure and find those constant speeds? The same way we've done lines since pre-calc, except now we just have this parameter t that we have to introduce. So for example, my x-coordinate changes from 5 to 2. So it increases by 3. What time frame do we want to give for that? We can pick one. It actually doesn't matter. The easiest one's probably 1 second. Let's just assume that we start at this point and 1 second later we end at this point. So that means my delta t was 1 second. In 1 second, my x-coordinate went from 2 to 5. So what is my parameterization of my x-coordinate? Well, my x-coordinate started at 2 and then changed at a rate of 3 for that period of time. So when t is 0, I'll get 2. When t is 1, I will get 5. So in general, this was just some sort of starting x naught plus the change in x naught. So you could say x1 minus x0 times t. And we can use that for all of the coordinates now. What is our y going to be? So y starts at 3 and then goes to negative 2. So what's our change in y? We have to decrease by 5 over that 1 second. And you can check again. When t is 0, our y-coordinate is 3. When t is 1, our y-coordinate will be negative 2. So pretty easy to parameterize lines. Go ahead and do the z-coordinates by yourself for the homework. So that shouldn't be too bad at all. Okay, so the next one I want to do, I do want to add one note. I think I mentioned this yesterday. I'll send an email out with some of these notes as well. So skip number, I think it's number 1, yeah, on homework 14. It's a mixing problem. If you want to try it and want to try to work it out yourself just for the practice of doing that mixing problem, feel free. Otherwise, I don't think mixing problems will be a big thing on the final, especially since we asked a mixing problem on the last midterm. And since the final, the short answer questions are going to be on new stuff, it would have to be a multiple choice mixing problem, which could be done. Could be, we could give you a statement about a mixing problem and then ask, which of the following differential equations models this? And there might be one question like that on the final. I don't see us writing more than one question on a mixing problem, on mixing problems for the final. But feel free to skip it. I won't grade it for this one. I want you guys to focus more on the parametric stuff and the arc length stuff. Okay, so let's do one arc length one just to get warmed up. And it says we're given a function y is equal to square root of x minus x squared plus arc sine of square root of x. And let me double check this real quick just to make sure. So I pulled this one out of the book and it was from the section on the book that says find the exact arc length, which means we should be able to do this by hand. Yeah, and it is arc sine of square root of x. Wanted to make sure I had it written down correctly just because, one little typo in terms of writing it down and, the integrand isn't going to work out very well. And then you can't integrate anything. So We want to find the total length. One thing we actually need, though, is total length between what? And it actually doesn't specify. So if it doesn't specify, there should be some sort of natural length of this curve. And primarily because the domain of arcsine is -1 to 1. So what's that tell us? The input for our arcsine in the function is square root of x. So we would have to intuit that we need square root of x. Whatever goes inside the arcsine has to be between -1 and 1. And of course, squaring both sides. What do we get? Is this correct? So not quite. You kind of just have to imagine that squaring both sides, unfortunately, it would change the inequality and just give us one statement about x being less than 1. Our lower bound in this case should be, of course, 0. Since I can't stick anything less than 0 in a square root, that would be our next consideration. So arcsine was kind of just the first one I saw. We actually need to consider the natural domain of everything in here. So that square root restricts our domain to positive values, 0 to infinity. The arcsine means we actually have to stop at 1. We should probably check, are there any other domain restrictions coming off this guy? So we would need x minus x squared. Has to be positive. And so if you remember how to do these from pre-calc, one way we could do is we could just graph it actually. You could do a number line test based off of like our calc 1 or pre-calc number line tests to figure out where this function is positive. The other thing we can do is just graph this. It's a parabola with zeros at 0 and 1. Hopefully everyone can see that. And since it's a minus x squared, it's going to go like this. It's going to be opening downward. So where is this function positive? Between 0 and 1. So that's our domain. And remember that our arc length formula is just square root of 1 plus dy dx squared. And we had our bounds from the domain of the function. So the only other piece we need is dy dx. Then we got to square it. Function's a little messy, so let's go through the computations. Let's see what we get. We will have 1 divided by 2 square root of x minus x squared times the chain rule gives me 1 minus 2x plus derivative of arcsine is 1 over square root of 1 minus the inside function squared times the chain rule times the derivative of square root of x gives me a 1 over 2 square root of x. So looks a little chaotic. Let's try to see what kind of simplifications we can do. And remember, we also got to square this guy. Let's see. So this is going to be 1 over square root of 1 minus x. I'm going to put the 2 out front times the square root of x. So nicely enough, since the square root of the x is already underneath the square root, we can essentially just multiply underneath those square roots. And lo and behold, looks like we have a common denominator. So of course, product of square roots, I could write square root of the product of those two factors and distribute. And then our common denominator gives us an ability to add in the numerators, and we get 2 minus 2x over 2 square root of x minus x squared. And then lastly, we can divide the 2's out. So remember, we got to factor the 2 out from both. So 1 minus x over square root of x minus x squared. And there's one more simplification we can do. You guys may not see this. This is a sort of a less common one. It will save us some time in the future. So this is probably a good enough simplification if you guys wanted to move forward. Square it. Wouldn't be too bad because we would square out that denominator easy. And then the numerator got to FOIL out a little bit, but hopefully you guys are getting good at that at this point. If we wanted to try to simplify it, this is 1 minus x divided by, we can refactor this denominator. So I'm just noticing that the denominator factored as 1 minus x times square root of x. So since I have this factor of 1 minus x in the denominator, it's a square root. But if we refactor it, then this is 1 minus x to the 1 divided by 1 minus x to the 1/2. And so we can get square root of 1 minus x over square root of x. And now, that's a pretty nice expression, especially if we have to square it. So let's go ahead and get a new page here. So our length was this guy. Our dy dx, let's go ahead and square it, is then going to be square root of 1 minus x over square root of x squared. And nicely enough, 1 minus x over x. And so when we plug that in, our integral from 0 to 1, square root of 1 plus 1 minus x over x dx. So all of these problems, if you have to do them all by hand, you'll kind of notice that a lot of the way this formula is worked out, because it's 1 plus something squared under a square root, it's either going to work with like a trig sub sometimes, or these functions are going to be cooked up in such a way that you kind of have to do a bunch of algebra, so then it'll simplify nicely in this expression. So we've still got some more algebra to do, and then the integral should be pretty straightforward. So we could write this as x over x if you want, and then it'll cancel that x, or you could simplify this guy on the right and write it as 1 over x minus x over x, which is 1. And so now we see, what do we have? Ones will cancel, and I'm just left with 1 over square root of x dx. Everyone follow that? Did I go through that too fast? Did you guys catch up on the last page? Was anyone still writing or need to see the other page? Cool. And then, of course, the integral of that is going to give me, 2 square root of x as the antiderivative evaluated between 0 and 1. And so we just get an arc length of 2. Any questions on that? So remember those two formulas for our arc length. Practice them. I'll try to give you guys a little bit of heads up over which one we will wait. Maybe which ones might appear on the midterm. Usually, typically in Calc 2, we emphasize this one a little bit more. Historically speaking, this one always comes up in Calc 2. This was kind of a Calc 2 finagling the way we kind of come up with this formula without having to do parameterizations. But since we're introducing parametric curves more now in Calc 2, we do have both of these formulas. So if you're parameterized, you get this guy. If you are not parameterized, so that's A to B. I'm going to use different letters. So this A to B is our T's. If we have it written in terms of Y, in terms of X, we saw yesterday how we can reduce our formula down to this guy that we just used. And of course, the bounds here are the bounds in terms of X. So remember those two. You'll work with them on homework 14. I think the problems, looking over them, they weren't too bad. So they should all be doable. Hopefully not take too long as well. Any questions on that, on arc length? Okay, so we've got one more thing to catch up on, and that is average value. It's real easy. You guys ready for this? All right, here we go. So for a function, let's say an integrable function, f on some interval, a to b, then the average value of f is the integral of the function over that interval, and then you just divide by the length of that interval. Nothing tricky at all. The way you can kind of think about this, well, if I have a set of numbers, what's the average of those? How do we compute the average? I add up all the numbers and then divide by 4. Divide by the total number of numbers. So you can kind of think, if I have a function, how do we find the average value? Well, we could do this Riemann sum thing and divide it all up and take, finer and finer Riemann sums. And I could compute the heights. So you could have this height plus this height plus this height, and then divide by the total length that these boxes span over. And of course, as I take the limit, the box is going to 0, we essentially get this. If I want to, the integral analogy, we're adding up an infinite number of values of the function. So the y values, we're adding all these up, and then we're dividing by sort of the total length, the total number of values that we added was between b and a, the length of the interval. So really nothing fancy there. So for example, average value let's say 1 plus x squared on minus 1 to 2. You just integrate that function between the bounds and then divide by the length of the interval. So right endpoint minus the left endpoint. And so we get 1/3 times the evaluation of the integral. And what do we get? 1/3, 2 plus 2/3 minus -1 minus 1/3. And then you just got to do the arithmetic. So what do we get? 1/3. 2/3 is 6/3 plus 2 gives me 8/3 minus. Did I miss that? 2 cubed. I thought we already had an 8/3. So let's see, 6/3 plus 8/3 gives me 14/3 minus. So -1 is 3/3. It's minus 4/3. Minus minus gives me plus a 4/3. So it looks like we are getting 18/9, just 2. Average value. The average value of a function, the way you can think about it is, if I have a function, well, it's moving up and down as x continues. As x goes to the right, the y values go up and down. You want to kind of think, well, what is the average height that I'm reaching? How high on average is this function? And that's going to be the average value. So essentially what it gives us is some sort of line or some sort of average where it's kind of like the area under this rectangle is the same as the total area under the curve. It's sort of a geometric way you can think about it. And then I guess the last thing we can ask on this is the mean value theorem. So let me write that down real quick. So the mean value theorem for integrals says that if f is continuous, on some interval, then there exists a c value in that interval such that f of c times the length of the interval is equal to the integral. Sorry, was that on the screen? So if f is continuous on the interval, then there's going to be some constant, some x value, where the value of the function times the length of the interval is the total area. So what's that mean in terms of the context I was just saying? Let's see if we can get this all on the screen here. So the average value, you kind of want to think, what is the average value that this function achieves? And another way you can kind of think about it is, well, the average value should be the height of a rectangle that should have the same area under it as the total curve. What's the mean value theorem for Calc 1? Calc 1 says if I'm looking at derivatives, then the slope of the secant line between the starting and end points, there has to be some value in between those where the slope of the derivative matches that. This is kind of the converse of that. This is simply saying, well, if I compute, you can kind of think, well, what's going to happen if I divide this b minus a over? This is saying that f of c is equal to the average value. In other words, not only can we compute the average value of a function, but there has to be some point where the function reaches that average value. All it's saying here, so c is the x value, where f of c is the average value. In other words, right, because my function is continuous, I'm not going to draw the average value box way up here. That wouldn't make any sense because the function never even gets that high. I wouldn't draw the box way below the function either because the function may not be that low. There has to be some point that if I'm traveling along this function that I actually reach the average value. That's all it's saying. And there might be more than one, just like in the regular mean value theorem. There could be more than one point where the slope of the tangent line matches the slope of the secant line. And just like here, there's going to be multiple points where the function actually attains is at the average value. So nothing too complicated there. Let's go ahead and solve for this for that last function. So we had f of x is 1 plus x squared on minus 1 to 2. And we found that the average value was 2. If we want to, say, find c that satisfies the mean value theorem. So if you see a problem like this in the homework or on the WebAssign, all this means is it might just give you a function and say, find a c that satisfies the mean value theorem on this interval. First thing you should always do is compute the average value. And once we compute the average value, how do I find c? We're just looking for where f of c equals the average value. So nothing too complicated there in terms of solving that. X squared equals 1. And we found 2 points. I guess I could have put c's in there, but yeah. So it looks like we start at the average value and then at 1, somewhere in between the interval. So at x equals 1, we are also at the average value as well. Any questions on that? So again, probably the big things with these guys were just going to be techniques of integration. I mean, the hardest thing we can really throw at you with an average value problem would be to have a harder function to integrate. And even, finding these C's, I don't know how much we're going to ask about something like this because it's not really a calculus problem. Once you find the average value, the rest is all just pre-calc, it's all algebra. Any questions? Arc length, average value? All right, so let's talk about polar coordinates. Polar coordinates are a way of modeling the plane with let's call it a circular grid. Think of like the logo for the UN, or like if you were standing at the North Pole. If you were standing at the North Pole and looking down at the coordinate system, it would look like this. So pardon my circular abilities. And then of course there would be radial lines going out. And you can kind of see that, well, at any point I have in space, it's going to be on some sort of arc. It's going to be on some circle of a certain radius. And it's going to also be on some sort of line. And it's essentially how we model it. Let's see, let's get some other colors since we're graphing. So what we're going to do is we're actually going to call those our angle. So our R is going to be our radius. And our theta is our angle measured from the positive x-axis. So we still kind of think of x and y are hanging out there, but we're not going to use x and y to model points. They're kind of just giving us the framework of saying, okay, well, I am on the plane. So what r is going to measure, if we have some point in space, I want to know how far away we are from the origin. That's going to be the r value of this coordinate system. Then the other thing we're going to measure is the angle of that ray, measured from the positive x-axis. And we're going to call this point as having coordinates. We're going to list them in as ordered pairs, just like x and y, but it's going to be r theta. So it should be given in the context if we're told we're using polar coordinates, because an ordered pair could be polar, could be rectilinear. It's going to have to specify. So the best way to do it is to kind of just start with some examples. So let's say we have our plane, and so let's pick some points. And these are going to be given in polar coordinates. So 1, 5 pi over 4. Let's call this point A, point B, 2, 3 pi. So how do we plot something like this? The way you want to do it is you kind of want to start along the positive x-axis. So just like if I was plotting x and y coordinates, you might go, if my x coordinate was 3, you would count over 3 and then up y, up to your y coordinate. With polar coordinates, you kind of want to count over by your radius. So remember, it's r theta. So our r is 1, so we're going to go over 1. And now theta is 5 pi over 4. So you want to think of just rotating around the circle or walking along a circle of radius 1 and go to an angle of 5 pi over 4. So you would start here, you would walk around to 4 pi over 4, and then to here, to 5 pi over 4. So that would be our point A. B, what do we want to do? It has 2, 3 pi. So we're going to walk over 2 on the x-axis, and then we've got to go around, how far? We've got to go around 3 pi. So all the way around the circle is 2 pi. And then we need to go around another pi. So B just ends up there. So we can kind of draw that out if you guys want. Let's use some color. And then, of course, it's going to trace around a second time and then end up there. So one of the problems with polar coordinates is that, well, we didn't have to have 3 pi here. I could have had another point two pi, and then there I'm just walking over 2 radius, and then we're going around that circle of radius 2 to pi. So B and C are actually the same point. And this happens in polar coordinates just because theta, our circles, are periodic. So we often restrict our theta between 0 and 2 pi. And we often restrict our radius as positive, 0 to infinity. Not always. But we can at least model every point in the plane with a theta between 0 and 2 pi and a positive radius. Let's see a couple more. So what happens if we have a negative radius? So something like minus 3 pi over 4. So there's a couple ways to do this. If your radius is negative, one thing you can always do is just assume it's positive to start with. So go over 1, 2, 3, and then go to 3 pi over 4. So we'd go around here, and then make it negative. So we'd be on somewhere down here on this sort of circle of radius 3, and then down here. The other thing you can do is, instead of walking to a positive direction on the x-axis, since the radius is negative, we could go negative 1, 2, 3. And the 3 pi over 4 is still a positive angle, so we still got to rotate in the correct direction. We're still rotating counterclockwise, so we would go 3 pi over 4 from that point, which would end up at that same point. And then I was also kind of bring up, well, what happens if our radius is negative? Let around e. I could say something like 2 negative 2 pi over 3. So a negative angle just means we are rotating in the opposite direction. So in this case, our radius is positive. We're going to walk over 1, 2, and then now I'm rotating minus 2 pi over 3 along that circle of radius 2. So we're going to about here. So a negative, no, sorry, 2 pi over 3. I was doing pi over 3. That one's not right. So we would go over 1, 2. That's pi over 3. 2 pi over 3 gives us somewhere over here. So that's our E there. Any questions on that? So really you want to think about it like all your unit circle skills from pre-calc play a role. You're really just thinking of what's my radius of the circle? What radius am I at? And then how far do I want to rotate around that circle to find my points? So just like we have functions y as a function of x, we can now model functions with these r and theta coordinates. Let's see. Let's pause that for a second. Let's actually convert some things. Let's come up with some formulas that will help us. In converting things back and forth. I want to do these first. So that way when we do functions, maybe we can convert some of these functions themselves back and forth between Cartesian and polar. But we also kind of want to get a sense of just how to straight up graph a function in polar coordinates. It's kind of similar to parametric equations. You kind of just have to plot points as theta progresses or as r progresses. Okay, so well, if I have a function or excuse me, if I have a point and I'm told, let's say r was, let's give our coordinates, r theta is 2, and then let's say 2 pi over 3. How would we find our xy coordinates for that? Well, I know I'm on a radius of 2, and so I'm on a circle of radius 2, and then we rotate 2 pi over 3. So we're at 60 degrees, or excuse me, 120 degrees, 60 degrees reference angle. Our point is there. So our radius was 2, and our angle 2 pi over 3. So you just got to remember all your special triangles. If I wanted to find my xy coordinates, well, what's the x coordinate going to be? My hypotenuse, nicely enough, is always given by the radius. Then my x value, well, this is my x value. If this is my angle, this is my reference angle here. Let's call this, well, let's call this theta. Let's call this alpha as our reference angle. Then what is my x value? My x value is just going to be r times, what trig function do we want to use? Cosine, right? Cosine of theta gives me my x over r. So x is going to be r cosine theta. Likewise, my y, r sine theta. Sine of theta gives me y over r. So all we got to do is remember all of our trig, our special triangles, our unit circle, and then we can compute our x and y values. So what is my x going to be? X is going to be 2 times cosine of 2 pi over 3. So you can draw your reference angles. We have 30, 60, 90. Cosine of 60 degrees gives me 1/2. So we'll get 2 times 1/2 for our x coordinate. And of course, 2 times root 3 over 2 for our y coordinate. And so our xy coordinates are going to be 1 square root of 3. So not too bad. We can essentially use that for anytime I want to convert polar to Cartesian coordinates. If we wanted to go back and do any of these points, we could essentially use that formula. Once we can compute sine and cosine of theta, multiply that by your radius, and you'll get your x and y coordinates. Conversely, if I'm given a point in rectilinear coordinates, if my xy coordinate is 1, 1, 1 minus 1, how do we find polar coordinates for it? So 1, 1's an easy one to graph. 1 minus 1. Let's go over 1, down 1. And we need to come up with the radius as well as an angle. Either a negative angle or, of course, multiple angles will work depending on where we want it, 0 to 2 pi, or if we want to allow, minus pi to pi. Well, the radius should be easy. If my point has coordinates x and y, what's the radius going to be? Let's write it up here. Pythagorean theorem. So my radius is just x squared plus y squared. What about the angle? The angle's a little trickier just because we want to use trig functions, but inverse trig functions have restricted domains. So we essentially write it as, well, if I can give an x and y, what trig function relates x and y based off of the angle? It is tangent. And we're going to leave it as that. Tangent of theta equals y over x. We don't want to use arctan. Like, it kind of want to think about arctan. Theta is kind of like arctan of x over y if we wanted to solve for our theta. But arctan, remember, has a restricted domain, restricted range. So we want to allow our theta to be anywhere from 0 to 2 pi. So if we keep the equation in that form, that kind of tells us that we're looking for theta that could be anywhere in that range. And of course, I guess if we wanted to solve for r here, you can take a square root. So these are our helpful formulas. These are going to be something you're going to probably want to memorize. Hopefully it's not too bad. I mean, r should be pretty straightforward, and the x's and y's you should be pretty familiar with at this point. And if not, hopefully by the time you've done a few homeworks, you kind of just know them. So what is our radius here? We can just compute. R is going to be square root of 1 squared plus negative 1 squared. So square root of 2. And what is our theta? So I know that we have this equation. Tangent of theta is y over x. So it'll give me minus 1 over 1 is minus 1. And we need to know when tangent of theta is negative 1. And so from this, when we have this equation, when you're solving it, remember all seniors take calculus. Tangent is negative in the second and fourth quadrants. So that means theta is going to be 3 pi over 4 or 7 pi over 4. And of course, we could come up with a lot more depending on which direction we're wrapping around the circle. And so this is where you have to kind of use the actual picture, use the actual point, because 3 pi over 4 we know is in the second quadrant. And since that's not where our point is, we know that our answer is going to be 7 pi over 4. So our polar coordinates for 1, 1, our r theta is going to be square root of 2, 7 pi over 4. Equivalently, since I can add and subtract 2 pi to theta, could just have minus pi over 4 if you want to allow negative thetas. Any questions on that? So at least hopefully the formulas and stuff that are coming up is nothing too new. And this stuff should all be hopefully basic, kind of just pre-calc refresher of the unit circle. But now we want to see what happens with curves. What happens when I have equations of r and theta? What type of curves do we get out of that? What type of functions? So curves in polar coordinates. Well, let's start off with easy ones, like constant curves. If I have curves like y equals 2, it's pretty easy. It's a horizontal line. I go up to 2 on my y, and I know y is constantly 2. X can be anything, so we just get a nice straight line. Conversely, if I said x equals 3, I know I count over to 3 on my x. This is where x has to be. and y can be anything. So we get that line. What about, so then r equals 2. How's that going to be drawn? What does it tell us? What information does that give us about the points, or the set of points that satisfy this? Well, all it is saying theta can be anything. I have no restrictions on theta, but it's saying that my radius has to be 2. So if my radius has to be 2, I know that I count over 2 on my x, but then theta can be anything. So I would walk in the direction of theta, and we would just get a circle. So this will be my best circle I can get. Ooh. Little oblong. But anytime I have r equal to a constant, this is saying what geometric shape has a constant radius? Circles. So r equals 2 is a circle of radius 2. Of course, r equals 1, circle of radius 1. What about constant thetas? So what if I say theta is equal to pi over 4? What are those kind of curves going to look like? Well, now it's saying my radius can be anything. I can go radially outward, but my angle has to be a fixed pi over 4. So our pi over 4 angle is a 45 degrees. And now, so we're going to be at a 45 degrees, but then my radius can go outward and inward. So my r can get bigger. I can have a larger radius away from the center, or a negative radius away from the center, as long as the reference angle, the angle, is pi over 4. So our different points might be radius of 1, pi over 4, radius of 3, pi over 4. If we go negative, radius of negative 2, angle pi over 4. Point would be there. So all of those points are going to be on this line. Likewise, we could have, let's say, theta equals, let's use a different color. What do I want to say? 5 pi over 6. So what is that? That means my theta, I go 5 pi over 6, and then my radius can be anything. So if I go 5 pi over 6, depending on my radius, this one might be 1 5 pi over 6. Up here, maybe 3 5 pi over 6. Would be that point on that line, and then of course we could go negative. So this kind of gives us our polar grid with circles and then radial lines through the origin. So let's summarize that. R equals constant is a circle. If we have theta equals a constant, is a line specifically through the origin, though. Another thing we could do to try to see this is that, well, we could convert back to rectilinear coordinates. If I have r is equal to 2, for example, and we want to convert back to rectilinear coordinates for an equation or for a function, all we have to do is do the same process we were doing for individual points. And we had that equation. So our r is square root of x squared plus y squared. Of course, if we allow r itself to be negative, better formula might be a plus or minus there. And since it's plus or minus, we could recover our standard equation of a circle based off of that. The thetas, I don't know if they'll work out quite the same way just because of the arctan restriction we have. If I have theta is equal to pi over 4, well, I know that tangent of y over x is equal to my theta. So what we have is tangent of, sorry, I read that wrong. Tangent of theta equals y over x. So what we could do is then take the tangent of both sides. And I'll say tangent of theta is tangent of pi over 4. And I know that tangent of theta is y over x. Tangent of pi over 4 is 1. And then my equation, we can recover y equals x. And we saw that nice 45-degree line. The reason we use polar coordinates, though, is because now there's a whole new family of curves that we graph in polar coordinates that would otherwise not work very well in rectilinear coordinates. Let me see, let me find my examples. Here's one. So other than constant curves, we often usually write, y as a function of x. For polar coordinates, we most commonly write r as a function of theta. I guess that's a little backwards in some sense, since the coordinates are listed as r theta. The r depends on theta, whereas, of course, x, y, we have our y depending on our x. So we usually have polar coordinates r depending on theta, and if I say r is equal to 2 cosine of theta, we want to know, what does a graph of that look like? And so since we have this restriction, this relationship between r and theta, best way to do it is to draw a graph, or excuse me, make a table to draw the graph. So we've got our theta, and then we've got our r. Well, so let's start off, theta equals 0, what's going to happen? And actually, this is kind of a common graphing technique for polar coordinates. I would say always start with your theta equals 0, and then move around the circle, right? The way we want to graph it, you want to think of it as kind of graphing around the circle as theta, the angle changes, but as the angle changes, the radius will change. So it can do some fancy things. When theta is 0, what is my r? Cosine is 0, which is 2. Let's go in increments of pi over 4. Are usually pretty nice to count in for your angles. So pi over 4, we get 2 times cosine of pi over 4. And what is cosine of pi over 4? Root 2 over 2. So we'll just get root 2. So now we kind of got to imagine, okay, this was a circle of radius 2. Draw some dots just to help graph this. If this is my circle of radius 2, how big is square root of 2? It's about 1.5. So now I'm at a 45-degree angle, and I got to go out about 1.5. So maybe about there. Then we do, let's go with pi over 2. Pi over 2 means I'm pointing straight up. So I should be walking straight upward as my angle. But what's the radius? Radius is 0. Anytime there's a radius of 0, we are right on the origin. And then we keep going. So 3 pi over 4. I'm pointing now this way. You can kind of think of it as just maybe a little arrow if it helps guide you, since our angle now is 3 pi over 4. And then we want to know, what's the radius? How far am I walking? What is cosine of 3 pi over 4? So 3 pi over 4 is in the second quadrant. And cosine of 3 pi over 4 it will end up being negative. So my reference angle is still pi over 4, but because of that negative, we'll get a negative square root of 2. This is where it gets a little funky, because now we've got these negative r values. So I'm pointing in this direction, and my 3 pi over 4, but now I got to go a negative radius. So I'm going backwards along that line. So we go a negative square root of 2. And so we'll be about there. And if we keep going, our last one is pi. And cosine of pi is negative 1. So we'll be at negative 2. How do we graph that? So pi, now we're pointing along the negative x-axis. But since I'm walking a negative radius, we go in the negative direction. And we're actually back at where we started. So this graph ends up being a circle. On the right side of the plane. The other thing you can kind of do is think about, well, what's happening to my angle as we change? So if I'm starting at an angle of 0, my radius is 2. As my angle increases, what's happening with cosine? So let's draw all that real quick. And since we're starting at 0, so cosine looks like, starts at a peak and goes to 0, hits a valley, and then comes back up and ends at a peak. And so my x-axis is my theta. What's going to happen as my theta changes? So you can kind of imagine, I guess this would be the radius then. So my radius should start, 2 cosine theta is going to have a amplitude of 2. So my radius is 2, but then as I rotate, the radius, the distance from the origin, starts to decrease. So as we are rotating, this radius decreases, and then we get here at 45 degrees. And then as I keep rotating, what's happening to the radius? The radius is dropping now to 0. So we're rotating, so we're pointing at that point. I don't know if you guys can see this. Pointing at that point, and then as we rotate around, as my angle rotates around, the radius is dropping to 0. Sorry if my hands are getting in the way of the light there. And then as I keep rotating, even though now I'm rotating and technically I'm pointing in this direction, but the radius is now negative, so I walk in the opposite direction, and then it traces around. Can you guys see that? So these are the types of things, this is going to be the newer thing of practicing these. When you first learn polar coordinates and start graphing some of this, take your time with it. Plot as many points as you can and kind of think about what's happening as my angle changes and how the radius is changing to get used to graphing some of these guys, because they can get kind of weird. Let's do one more. I think we got time for it. Other things we like to draw, 1 plus sine of theta. I think this one's called a cardioid because it's going to look like a heart. So again, let's start theta at 0. So we're pointing along the x-axis. What's my radius in this case? Sine of 0 is 0. So we're just going to get 1. So I'm angle 0, radius is 1. And let's move around again by pi over 4. Sine of pi over 4 is root 2 over 2, so we get 1 plus square root of 2 over 2. And how big is that? So square root of 2 over 2 is, let's see, about 0.75. So square root of 2, usually good to approximate with 1.5. So square root of 2 over 2 is about 0.75. So about 1.75. So it kind of jumps up, it looks like, to a radius of 1.75. So again, my angle 45 degrees, and then I walk this distance. The radius is 1.75. What's going to happen at pi over 2? Pi over 2 sine has a peak, so we'll have 1 plus 1, and we'll get 2. So we'll be pi over 2 straight up, radius of 2. Let's keep going. 3 pi over 4. Angle is out this way now. Sine of 3 pi over 4, so sine is positive in the second quadrant. So it'll still be a positive square root of 2 over 2. So we'll get another 1.75 at 45 degrees. So something like there. I think my angle's a little off. It's not quite 45 degrees with either of those. Try the best you can to graph these. Really, the overall shape is kind of the most important, right? Just to kind of see what it's behaving, how the radius is behaving as we're rotating around. So pi, we're pointing horizontally on the x-axis. What happens to sine of pi? We get 0. So we just get 1 again. So we're kind of back here. So it looks like as I'm tracing around, we're going up. The radius is increasing, kind of like an oblong shape. And then we're coming back down. So far, nothing too fancy. Let's keep going. So we've got 5 pi over 4 next. And that's where sine is going to be negative. So the nice thing about doing 5 pi over 4 increments, or pi over 4 increments, is that your sine and cosine are always going to be square root 2 over 2, positive or negative. You just got to be mindful of the quadrants. So it'll be 1 minus 0.75. So it'll only be about 0.25. That's pretty small. So our radius went from 1 to 1/4. And now we're pointing at a 45-degree angle. So we're like here. So it's going to come up, around, and then it's going to curve real sharp here. And then what's going to happen at 3 pi over 2? Sine is -1. So 1 minus 1 gives me 0. We're actually back at the origin there. It's going to come down, hit that point at the origin. And then if we wanted to continue our table, so what comes next? 7 pi over 4, and then 2 pi. So 7 pi over 4, again, sine is going to be negative. So we'll get 1 minus square root 2 over 2, and another 0.25. So we'll be at our angle, 7 pi over 4, small radius of 0.25. And then, of course, at 2 pi, we've gone all the way around the circle, and we'll be back at 1. So we get this upside down heart-looking thing. Where it's going to start off, come up, and decrease as soon as I get that angle bigger than pi. It's going to start to be real small, and then bounce, and give us something like that. Any questions on that guy? So Monday we'll practice a lot more with these. There's a project on Monday for mashing and graphing these you guys selves. I think it'll be good practice just to get used to doing these polar coordinate graphs and thinking about these graphs and these functions in polar coordinates. Because then Tuesday, Wednesday, we'll be finishing up essentially the final topics are arc length and area. So now if I wanted to find the area inside this upside down heart looking thing, how do we do that? Of course, we're going to want to integrate, but we've got a little bit more to do with our area differentials before we can actually integrate properly. So we'll talk about that next week. Have a good weekend. If you want, stick around for a few minutes if you have any questions.
Hey, I got a question on the WebAssign for today.
Sure.
Number 4. I don't know if you have it pulled up or I can read it to you. But
WebAssign pulled up. Let me just pull up the assignment. Let's see, 731. Oh yeah, this one's confusing. It's worded really weird. We were talking about this in office hours last night. A few other students had questions. Yeah, let me show you what this one's talking about. It's weird by the way it's phrased because it sounds like some of the ones we've been doing in class where we've talked about how some functions can have 2 different tangent lines at a point, right? Where some functions will do something like a figure 8, and now at one point I have 2 different tangent lines we have to find. This is not what this question is asking, even though it kind of sounds like it. What it's asking is, it's essentially saying that we have some curve, and I don't know what the curve looks like, but so for example, let's say I have some curve. Really what it's looking for is the tangent lines passing through the point, not the curve itself. That's given. What's your point that's given?
12, 9.
12, 9. And then what are your functions? So your x?
X is 9t squared plus 3, and y is 6t cubed plus 3.
T cubed.
And I just like, there's only one t that I can see.
Yeah, no, it looks like because there's only one t that this curve passes through, but what it's asking is is for the tangent lines to pass through this. It's very subtle the way it's phrased, and it's kind of confusing. So really what we want, like I could have specified a point outside of the curve, and then really what it's kind of asking for is what tangent lines will pass through that. So we're kind of looking for these 2 points for those tangent lines. Nicely enough, they do give us at least 1 point on the curve, but just as I kind of drew, I could have a point on the curve here. And of course, there's a tangent line that is tangent to that point. But then I could find a point over here is what they're looking for, whose tangent line will then pass through that point. So it's a little confusing because what we're looking for is a different point on the curve whose tangent line will pass through this point 12,9. So the way you want to think about it is you find your x prime and y prime. And so your dy dx is just t.
Yep.
And so what you want to solve for is essentially the equation we have. What do these tangent lines have to satisfy? It's just the point slope form. I'm writing that backwards. Y minus y naught equals t is our slope, x minus x naught. And this will hold for any 2 points, any points we choose on the curve. So the points on the curve, I know my x and y are given by the parametric equations. So you're going to have 6t cubed plus 3. Substitute that in for y. The point, your y naught, is going to be your y coordinate. And then you'll have your x parametric equation in for your x minus the x coordinate. So when you solve this out, I think, so you should find t equals 1. I think that's the point on the curve that passes through this. But you'll find another t value. Use that t value, which will be a different point on the curve, and then find the tangent line at that point. That tangent line will pass through this point as well.
Okay, thank you.
Welcome.